Okay, problem 36. Let's have the construction of shear moment diagram for frames. For the frame shown below, construct the shear and moment diagrams. Also sketch the elastic curve. So that's the loading condition. First, based on the loading, let's analyze portion AB. 8 kilonewton meter over this inclined member AB. The length of AB is 5 because this is 3, that's 4, so 5. Therefore, we equate it to equivalent normal load. So this is 8 kilonewton per meter over this 5-meter length. So we can resolve it into load components, normal and parallel to AB. So because the vertical distance is 3, horizontal 4, so the length of AB is 5. Therefore, Wn is, because if you call this theta, this is also theta here. Wn is 8 times cosine theta, which is 4 over 5. And W tangential is 8 times sine theta, which is 3 over 5. So that's theta, theta also. Wn therefore is 8 times 4 over 5, so that's 6.4 kilonewton per meter, while W tangential is 8 times 3 over 5, 4.8 kilonewton per meter. And for this portion here, this is a load over the horizontal projection. So the total load is 7.5 over the horizontal projection, but this member is inclined. Therefore, the load over the inclined member is 7.5 times 6. Then we divide that by the length of member BC. So we'll call the angle here as beta. And the slope is 1.75 vertical, 6 horizontal, which can be modified into times 4, 6 times 4, 24, 1.75 times 4 is 7. So the hypotenuse is 75. So this is 7.5 times 6, 45 kilonewton vertically. Then that 45 kilonewton should be divided by 6.25 to convert it into vertical load over this BC, WY. So 7.5 times 6 is 45 divided by 6.25 meters. The length of BC is 7.2 kilonewton per meter. Then from there, we can convert that into normal and tangential load again. So Wn1 and W tangential 1, where Wn1 is 7.2 times cosine of beta, and cosine of beta is 24 over 25, while W tangential 1 is 7.2 times sine of beta, which is 7 over 25. So Wn1 is 7.2 times cosine of beta, 24 over 25, 6.912 kilonewton per meter. W tangential 1 is 7.2 times 7 over 25, 2.016 kilonewton per meter. So we'll call this RA, R sub CY, then obviously summation forces horizontal, R sub CX is 0, but we will verify that later. So consider the whole system, summation of moment about C equals 0, clockwise positive, so we have RA times 10 equals 7.5 times 6 times 3 plus 8 times 5, because this is 5 meters and the moment arm is 8, 6 plus half of 4, 2, so 8. So RA is 45.5 kilonewtons vertically upward. That's a roller support. Then R sub CY, summation moment about the 0, R sub CY times 10 equals 8 times 5, 5 meters length of AB times 2, then plus 7.5 times 6, 3 plus 4 is 7. So R sub CY is 39.5 kilonewtons. Then, based on Wn and Wt, so Wn is 6.4 times 5 is 32. Then here Wn1 is 6.912 times 6.4 6.25, the length of BC is 43.2 kilonewtons. Then this is the tangential load WT, which is 4.8 kilonewton per meter. Then because it acts along the length of 5 meters, so 4.8 kilonewton per meter times 5 meters is 24 kilonewtons. Then this is WT1, which is 2.016 kilonewton per meter times length of 6.25. So the equivalent load is 12.6. Again, 2.016 times 6.25 is 12.6 kilonewton. So that's the equivalent tangential load, this one. And I just shift it here. So let's resolve 32 kilonewtons into horizontal and vertical components. 32 times sine of theta, 3 over 5 is 19.2, while 32 times cosine theta, this one, the vertical component, is 32 times 4 over 5 is 25.6. So we remove 32. We replace it by its horizontal and vertical components. While 43.2 times horizontal going right times 7 over 25 is, by the way, 24 kilonewtons. This tangential load here is resolved into horizontal and vertical components. So 19.2 is 24 times cosine of beta, cosine of theta. 24 times 4 over 5 is 19.2, while the vertical component of 24 is 24 times sine of theta times 3 over 5. So 24 times 3 over 5 is 14.4 downward. So that's it. Then we remove 24. We replace it by its horizontal and vertical components. Then for the distance, so half of 3 is 1.5 plus 1.75 is 3.25 meters. Then 3 plus 1.75 is 4.75 meters. This is 6 plus 2, so 8. Then the original dimensions. Then summation moment about C equals 0. Clockwise positive, so RA times 10. Then plus 9, this one, 19.2 times 4.75. Then equals 19.2 times 3.25 plus 25.6 times 8. Then plus 43.2 times 3.125. Then plus 14.4 times 10. Then 43.2 times 3.125. I almost forgot 14.4. So solving for RA should be equal to 45.5, just like this. Then summation forces Y equals 0. 45.4, which is RA plus R sub CY, or R sub C in this designation here, is equal to downward forces 14.4 plus 25.6 plus the vertical component of 43.2, which is 43.2 times 24 over 25, then plus vertical component of 12.6 times 7 over 25. So solving for R sub CY is 39.5 kilonewton, just like in the previous calculation. Then let's check R sub CX, summation forces X equals 0. So we have 19.2 R sub CX plus 19.2 plus horizontal component of 43.2, which is 43.2 times 7 over 25, then minus 19.2, then minus horizontal component of 12.6 times 24 over 25, or cosine of beta. Then the result is 0. So that proves that RCX is 0. So that's it for this portion. Let's continue this on the next slide. So now that we have computed in two ways the reactions, let's now consider the figure shown and the normal loads and tangential loads. So remember that this is also theta, and this shear here is 45.5 times cosine of theta. So 45.5, which is RA, times cosine of theta, which is 4 over 5, is equal to that value there, 36.4, while this normal force is 45.5 times sine theta, or 45.5 times 3 over 5. So that gives us 27.3 kilonewtons. So we now remove 45.5 because we need the shear force here for the construction of the shear moment diagram. So let's transmit 36.4, 27.3, and 6.4 times 5 is 32. Then 4.8 times kilonewton per meter times 5 is 24. Then call that shear BA, assume positive shear or going down. Then that's the normal at B. So that's also the moment at B. So shear BA is summation forces in this direction is equal to 36.4 minus 32. So shear in BA is 4.4. Since it is positive, that direction is correct. The normal at B is 27.3 minus 24, or normal B going left plus 24 equals going right 27.3. That's why normal at B is 3.3 kilonewtons. Then moment at B is equal to 32, or summation moments at B equals 0. Counterclockwise positive, so moment B plus 32 times 2.5, this is half of 5, so 2.5 is equal to 36.4 times 5. So solving for moment at B, it is equal to 102 kilonewton meter, and that is the sense. Let's now transmit NB shear BA and MB to this joint B here. So we have MB, this is counterclockwise, so it's clockwise on the next free body diagram. VBA is 4.4 downward, so it is upward here, and leftward NB, so it's rightward there. So that's shear in BC, which is perpendicular to BC, then normal at BC, and moment at BC, which is equal to 102 counterclockwise this time, because that's a very small segment at B. So at B, summation forces X equals 0 to solve for NBC. So we have shear BC, or 3.3 times cosine of theta, which is 4 over 5, minus, because 4.4 is up to the left, so minus 4.4 sine theta, 3 over 5. That's the sine of theta here. Then plus shear BC, it's going right, times 7 times sine of beta, which is 7 over 25. Then minus NBC, going to the left, times cosine beta, which was 24 over 25 equals 0. So simplifying, shear BC is equal to 24 over 7 of NBC, normal of BC. Call that equation 1. Then summation forces Y equals 0. Then we have 3.3 up times sine of theta, which is 3 over 5, plus 4.4 going up times cosine of theta, which is 4 over 5. Then minus going down, shear BC times cosine of beta, 24 over 25. Minus this is going down, the vertical component is small, so times sine of beta, which is 7 over 25 equals 0. Simplifying, 24 over 24 over 7, which is shear BC, transposed to the right, times 24 over 25, then plus NBC times 7 over 25, because these two terms are transposed to the right, then equals, the result here is 5.5. So simplifying, NBC is equal to 1.54 after this equation here. Then shear BC is 24 over 7 of NBC, 1.54. So shear BC is 5.28 kilonewtons. So now that we have found shear BA, which is 4.4, and shear BC is 5.28 kilonewtons. So let's then transmit this. So this is 39.5 times cosine of beta, which is 24 over 25. So the shear component of 39.5, this is the reaction CY, RCY, is 37.2, while the tangential component is 39.5 times 7 over 25, that's 11.06 rightward. So we remove 39.5. This is now the details of portion BC. So remember, normal BC is 1.54, so it is going left here. So when transmitted to BC, it's going right. The shear in BC is downward. Where is that? 5.28. So in member BC, when transmitted, it's going up 5 up to the left, which is 5.28. Then at the right end, we have 6.912 times 6.25, 43.2. That's the equivalent vertical load. Then 2.016 times 6.25, that's 12.6. That's the equivalent tangential load. Then the shear here is 37.92. Then we have 11.06 going right. So remember, this is 3.125. So consider BC. Summation forces tangential is 1.54 plus 11.06 minus 12.6, so it's 0. So that means this is in equilibrium. Summation forces normal equals 5.28 minus 43.2 plus 37.92, so that's also 0. So that means this body BC is in equilibrium. And summation moment about C is 102 clockwise positive plus 5.28 times 6.25. Remember, this is 6.25. Then minus 43.2 times 3.125. It is also 0. So that's okay. We expect moment at C to be 0. And here, at the last part, let's now construct the shear and moment diagram. So for the shear diagram, first we rise by 36.4. So shear diagram in kilonewtons, 36.4 minus 6.4 times 5 or minus 32 is positive 4.4. Remember, shear BA is 4.4. So it closes. Then shear BC is 5.28, I think. It was calculated in the preceding slide. Then minus 43.2 going down, so negative 37.92, then plus 37.92, so that closes. So the area of the trapezoid here, by the way, this distance is shear 5.28 divided by 6.912. Again, 5.28 divided by 6.912, the uniform equivalent normal load, is 55 over 72. The other way is you apply similar triangles to solve for this distance. 5.28 as to this distance equals 37.92 as to 6.25 minus this distance. So you'll get 55 over 72. But the shortest way is shear divided by uniform load 6.912. So therefore, this distance is 6.25 minus 55 over 72. That's the equivalent exact length. So this area is area of this trapezoid. It's 102. 1 half of 36.4 plus 4.4 times 5 is 102. Then this area is 1 half of 55 over 72 times 5.28. It's 2.0167 kilonewton meter. So this area is negative 1 half of 395 over 72 times negative 1 half of 395 over 72 times 37.92. That's negative 104.0167. So we are now ready to construct the moment diagram. So remember, moment at A is 0. This is positive decreasing. So it looks like that. The moment is 102. So that's 102. So it begins with moment BC also 100, positive 102. Then plus 2.0167 to 104.0167, positive decreasing. Then minus 104.0167, negative increasing. So that's moment at C0. So this is the moment diagram. And we are now ready to construct the elastic curve. So remember, this is a ruler and this is positive, so it is concave up in this portion AB, then also concave up in portion BC. But the elastic curve passes through C. At B, it falls a little because of the loading. Then because this is a ruler, it looks like that. So this is the construction of the shear moment diagram for this frame. I hope that you were able to follow the solution and the sketching of the elastic curve.